Hello. In this video, I thought I would just go over this rocket engine that I've designed and we've mostly built now for my university's rocket club, as well as go over some of the basic steps along the process as you begin to design your own rocket engine. So I've kind of broken them down. Excuse the notepad, Doc, but these are kind of the basic steps the way I thought about it. So the very first thing you want to do is just pick your propellants. And if you're at the amateur level or the collegiate level, this is kind of gated or limited by what you have access to, really, and what your budget, how big your budget is. So what we chose was ethanol and nitrous oxide, which are two very common propellants in the amateur liquid rocketry scene right now. They're easy to get a hold of because this is just like, you can get this from an automotive racing shop. Nitrous oxide, it's the same nitrous that, makes your car go fast. And then ethanol is pretty easy to source as well. Isopropyl alcohol is another option, similar to ethanol, pretty easy to source, like 99% purity IPA. And actually, it behaves pretty similar to ethanol. Propane is another option for the fuel. Again, easy to source, but it has kind of a low vapor pressure at like room temperature. It's vapor pressure or much lower vapor pressure than nitrous oxide, I should say. So it doesn't have the nice self-pressurizing property that nitrous oxide has, or it does, but not. It doesn't get you to a good pressure. Only like 200 psi or something in that range. At room temperature, so you probably still have to pressurize it with some inert gas, just like you would with any of the other propellants. There's a bunch more fuels I didn't list here. Pretty much any hydrocarbon that you could get your hands on. I mean, people use gasoline and whatnot, but you do want to think about, if you are going to use regenerative cooling, your fuel is most likely going to be your coolant, unless you use like a water jacket. Or like unless you use water as your coolant, you're probably going to be using your fuel as your coolant. So you want to pick a fuel that has good, heat capacity and won't vaporize in your coolant lines, unless you want that. But assuming you want it to stay liquid in your throughout the coolant channels, you got to think about that too. So ethanol is a good choice that a lot of people go with. On the oxidizer side, like I said, nitrous oxide is easy to get your hands on. So is gaseous oxygen. You can get it from like welding supply stores. But with gaseous oxygen, you run into the problem that if you want a high mass flow rate, because it's a gas, it's just not dense at all. So you need really big lines to not inadvertently choke your flow if you want any serious MDOT, any serious mass flow rate of GOX. You need very large diameter lines, and that gets annoying. And then coupled with that, you get very high flow velocities of GOX, which gets a little sketchy. You have to clean everything very well. Oxygen service, like clean everything to an oxygen, like the same level you would clean, anything. All your lines, all your fittings need to be, free of debris that would get accelerated very fast and could potentially trigger something bad, some kind of energetic event. And of course, you have similar problems with nitrous oxide, but you're going to be using the liquid phase of the nitrous, so it's a little less sketchy. The activation energy is a little higher for something bad to happen versus GOX is already a gas. But if your mass flow rates are low enough and you're willing to work around that, that's another good option. If you go to any sort of flight vehicle, though, the low density is really gonna hurt you. You're gonna need some crazy big tanks to store any amount, or super high pressure tanks to store any amount of gaseous oxygen. But it is doable, just not at very high mass flow rates. Liquid oxygen is another one. But you're taking that step into cryogenics, and all your valves and everything need to be rated for cryogenic use. So that has its own set of difficulties. But if you're willing to take that step, LOX is, just the best oxidizer. The next step is probably to pick a thrust level. So for this rocket engine, we picked 250 pound force thrust, which is about 1,000 newtons of thrust at sea level. And you can kind of tell this is a sea level nozzle. So the nozzle is optimized for sea level firing. That's because we're trying to make a vertical takeoff, vertical landing hopper vehicle. So we will never go very high in the atmosphere, probably never above a kilometer or something at most. But you have to choose for your vehicle. You know, if you're making a traditional rocket, an unguided rocket that's launching off a rail, you probably want a thrust to weight ratio of maybe, you know, somewhere around 3 or even higher. So you have to know like your fully loaded wet mass. Just work backwards. You know, you have your vehicle's fully loaded wet mass, and you know you want thrust to weight ratio of 3 or whatever. Then that will give you, you can sort of back out the thrust level that you need. If you're just trying to fire the engine on the ground, I would let your test sim requirement drive the thrust level you pick. I mean, there are a ton of other things that could drive it too. You know, the valves you have access to, how big you want your lines to be, the inert gas regulators you have access to. Basically, like in general, things related to your test stand could drive the thrust level as well if you're just looking to do ground tests with the rocket engine. You know, so like we're using like 1/4 inch sheet metal as sort of the plate that we thrust into. So 250 pound force is also kind of like the maximum thrust that still gives us a nice factor of safety there. So that sort of gated, the test stand also gated this our decision to choose to pick that thrust level as well. And then, like I mentioned, you want to consider the flight regime, like where this thing will be firing. So for us, we're only firing at sea level. So this you can tell this is a small nozzle, you know, optimized for sea level. So the flow should be fully expanded at, you know, 1 atmosphere of back pressure. So that's another decision. Obviously, if you're going to be going higher in the atmosphere, you know, 10, 20 kilometers, you might want a bigger nozzle that will be optimized for somewhere, you know, closer to where you're going to spend most of your time. The back pressure you'll spend most of your flight at, you know. So I would do that in RPA. I've mentioned RPA in previous videos. The nice thing about RPA is that once you do your analysis, I mean, I would use NASA CEA as well and compare the two, but they should be pretty close. And once you complete your analysis in RPA, it can spit out the entire contour of the rocket engine, including the converging and diverging sections, and then you can just revolve that around and get your geometry, which is very nice. You can import it directly into CAD. It'll output like a DXF file or something, and you can import that directly into CAD. Okay, so next I would pick an OF ratio, OF mass ratio. And I mentioned this in the other videos too. You can use NASA CEA and RPA, and they should agree with each other, you know, within 10% or whatever. Just good to check both. Generally, you probably, I mean, assuming you're trying to optimize for something, you probably want to optimize for you know, performance, typically specific impulse, which will lead you to a little bit fuel rich of stoichiometric, or you know, a significant amount fuel rich of stoichiometric depending. And then you may want to go even more fuel rich than that in order to bring the adiabatic flame temperature down, basically your chamber temp down for cooling. And RPA can do all of that. It has a whole engine cooling section, including, you know, regen cooling, film cooling. I think maybe it can do ablative cooling. I haven't looked at that yet, but you can, you know, mess around with that or create your own thermal sim. There are other options out there, but basically you want to pick an OF ratio that, you know, maximizes performance while not melting your chamber with the level of cooling you have. Or if you're running a heatsink chamber, you know, that you're just going to fire for a few seconds, then you have to do the like transient thermal analysis, because it's not going to reach steady state, but you don't want, you know, however long your burn is going to be, however many seconds your burn is going to be, you don't want to melt your chamber in that time. So that may push you towards a more fuel rich OF ratio as well. You typically never want to be ox rich. Yeah, I'll just leave it at that. And then coupled with that, I would pick the method of cooling your chamber. Like I mentioned, you could have a heatsink chamber that just fires for a few seconds, but that really limits your runtime, but they're simpler to make. And it's a good way, you can design it such that a heatsink engine can use the same injector as, you know, let's say you're designing an engine and you want to test just the injector. You can design it such that this injector can accept any chamber, whether it's a heatsink chamber or the regeneratively cooled chamber. So you can, you know, sort of create this, some people call it like a battleship chamber or battleship nozzle, to just fire for a few seconds, qualify your injector while you work on the, you know, main regen cooled chamber or what have you. There's also ablative chambers. I don't know too much about this, but I do know that, you know, you choose some sort of ablative liner that lines your chamber, and especially your throat. Your throat may have like a graphite, you may have graphite throat insert like what they use for solid motors as well. But you'll get some erosion of that throat, and of course your ablative liner will, you know, ablate away, and so that will limit you sort of to a single use per chamber. So what I recommend, and actually is getting more and more accessible with modern metal 3D printing, is just straight up do regen cooling. That's where you flow, I've talked about it in other videos, you flow typically your fuel or a different coolant through channels before it gets injected. So in this case, we have, you can see one channel here. So the fuel enters this volute here and flows up opposite the direction, opposite the hot exhaust direction. There are 49 channels. Let's see if I can hide some of these. But yeah, and it flows up these channels. You can see one here, and then gets injected here in this annulus around the pintle. So that's regen cooling. And the nice thing about metal printing is, you know, you can get these complex internal features that would be impossible to machine any other way. And, you know, I mean, tariffs aside, the metal printing is getting pretty accessible in terms of cost. So I would recommend, you know, pursuing this if you're interested in it. You may also need to employ film cooling or, you know, some kind of thermal barrier coating. RPA is not so good at thermal barrier coatings, but film cooling it can simulate pretty well. And what drives that is sort of, the way I think about it is just the hoop stress at a few locations. So like in the nozzle, both your temperature and pressure, in the expanding portion of the nozzle, the temperature and pressure drop. So this is probably not your worst case. Your worst case is either going to be the main combustion chamber where the pressure and temperature are the highest, but the heat flux isn't as bad because you have more surface area. And then the throat is where the heat flux is the worst. Even though the temperature has dropped a little bit, and the pressure has dropped a little bit, the heat flux is the worst. So I would, you know, look at the output of your RPA thermal sim, and look at the material properties. So for example, this is printed in aluminum, an alloy called ALSI 10mg. And so, you know, find a table. I'll link one for ALSI 10mg, but they're, you know, whatever you're printing it in or whatever material you're making your chamber out of, you have to look at the material properties. I chose to use the yield tensile strength for the hoop stress calculations. And you look at how it changes with temperature, and then you look at the temperature that's, you know, predicted at the throat, the worst temperature that's predicted in the chamber, worst temperature at the throat. Look at the material properties, do the hoop stress calculation, and then see what your, you know, margin is. and that will drive that will sort of drive the temperature limits. So for the ALSI 10 mg, I would recommend trying to stay under 600 Kelvin or under about 300 C, if that's the material you're printing in, because your yield strength really drops off a cliff after that. But you know, you have to do your own, like if your throat is really small, the hoop stress is not so bad, and so maybe you can get away with, you know, a higher temperature than that. But anyway, so those all go hand in hand, and that will decide whether you need film cooling or not. I think film cooling is a good idea, especially on Pintle injectors, and I'll talk about that later. But so we chose to employ, I think, 20% film cooling, which is pretty high. But you can see these film cooling holes here. Let's see if I can isolate the injector. So this is what our injector looks like, and you can see that we have 8 film cooling holes. This is the fuel, the sort of fuel dome part of the injector. So fuel flows through the cooling channels, flows up through these 49 holes, and then goes out through this annulus here, and also through these 8 film cooling holes. And we sort of were limited in number of holes by the diameter. You can see each of these is half a millimeter. So that was about as low as we could go with the drill bits and machines we had access to. And you can also see that they're countersunk at a 2 mil diameter most of the way. So you just have to peck through that last little bit at half a millimeter diameter. So I would recommend doing that if you're doing very small film cooling holes. I will put the caveat that we have not fired this engine yet, so I do not know how effective these film cooling holes will end up being. There aren't that many of them. I mean, ideally you'd have as close to a perfect sheet around the wall as possible. So the space in between these holes may make them not as effective as we'd hope, and also they're not perfectly on the chamber wall. But that's just another thing to consider. And then you also have to consider that any mass flow rate of fuel that you allocate to film cooling probably will not contribute much to actual combustion, because it's just extra fuel just going along the outside of the chamber wall, and you know there shouldn't be much free oxidizer, so probably most of it won't combust. You hope it doesn't, because really then it's not really film cooling fuel. But anyway, you can kind of ignore that in your you can't consider it as combustible fuel in your calculations. Okay, so next I would say pick an injector type. So for our engine, I chose a Pintle injector. Many people have done this. There's a lot of literature out there about it. There are certain design rules you want to stick to when designing a Pintle injector. That has to do with like the length of the post before you get to the pintle holes. And I'll link a couple papers that helped me design this Pintle. But these kind of injectors are known for their combustion stability, especially on larger engines. I'm not sure how well they scale down, so we'll see. We have, as I said, we haven't fired this engine yet, but a Pintle injector is also fairly easy to machine, and it doesn't require, like with some of the other injector types, like impinging injectors, you need the fuel and oxidizer streams to impinge at a specific point, and if you misalign the orifice holes, they just won't impinge and you won't get mixing. Whereas at the Pintle injector, you have a sort of a sheet of propellant coming out through this annulus gap, and then the other propellant comes out through these holes, and so you're guaranteed impingement. Like it's going to happen one way or the other. So that's a nice feature of Pintle injectors. It doesn't require quite the same level of precision that maybe an impinging doublet or triplet might. I have not designed one of these injectors before, so I'm may not be the best resource for that, but I can link a couple papers about these as well, and I'll link a couple papers about that helped me design this Pintle engine or Pintle injector. Sorry. There are certain rules you want to follow, like the length of the post before you hit the holes. So I'll link a couple papers on that in the description as well. Coax shear. This is another pretty easy injector to design. It's basically the case of one propellant goes through an annulus like this, and the other propellant just goes through a hole, and the propellants sort of shear against each other while both traveling downstream axially at the same time. So instead of having it, shoot out, it's just shooting straight down, and there's an annulus gap for the other propellant, and you probably have multiple, shear injector elements. Those are also fairly easy to machine and design, and you can buy if the inner holes are too small to machine, you can buy like little needles or something, and then and sort of bond them somehow to the injector face and inside of the annulus. And if you have multiple elements, you can kind of spread out the, it helps spread out the propellants throughout the combustion chamber, whereas with a Pintle you just have one singular Pintle element. Another thing to consider with Pintle injectors is whether you have a fuel-centered or aux-centered Pintle. In our case, we chose aux-centered because simply for ease of manufacturing, because our fuel is already flowing up through the cooling channels, so it sort of flows up the cooling channels and then goes through these holes, and it's already here above the fuel dome, so it's much easier to just inject it through the annulus gap than it would be. We'd have to pull out the propellant and inject it back through the Pintle tip if we wanted to do a fuel-centered Pintle. So it's much easier to just do an aux-centered Pintle since our fuel is already being used for regenerative cooling. This does mean, however, that since our fuel is ethanol and our oxidizer is nitrous oxide, the mass flow rate of your oxidizer is almost always going to be higher than the mass flow rate of your fuel. So that means there's a higher mass flow rate oxidizer essentially shooting straight out at the chamber walls, and it will lose some of its like circumferential momentum, like as it gets impinged on by the sort of cylinder of or annulus of fuel, but you do run the risk of shooting oxidizer at your chamber walls, which could you want some downstream cone angle as a result of the mixing propellants to hopefully not melt your engine. And then another consideration is keeping your propellants separate and contained within the engine. So that's what these O-rings are for. You can see we got one here, one here, one here, one here. We do not have any redundant O-rings or backup O-rings. In this design, we just didn't have the space for them, but that's another decision or trade-off you'll have to consider for your engine. There are a lot of resources out there that will tell you exactly how to design these O-ring grooves for gases, for liquids. I personally use the Parker O-ring handbook, which I will also link. Half Cat Rocketry has their own sort of design guide that's a little looser on the tolerances than the Parker O-ring handbook. But I found that if you machine it to the specifications of the Parker O-ring handbook and you use a lot of grease, liberal amount of grease, and you of course like deburr these edges and such, that you can get away with some pretty tight tolerances. I think Parker O-ring handbook in general for these sizes, it's about a 2 thou gap between the bore and the piston or whatever you want to call it. The inner piece and outer piece have about a 2,000ths. I think it might even be like 1,000th on each side. But those tight tolerances are, they do work. And then obviously like face seals are easier too, because you're just pressing up against, and the O-ring will take up a lot of the slack too, if you have slight deviations in your machining. But yeah, I'll link the Parker O-ring handbook. That was pretty helpful to me when designing this. So that's another thing to consider, is how you keep your propellant separate, and whether you're willing to accept the risk of not having a secondary O-ring in place or not. And then one other thing, the last thing I would mention is that you want to consider is how you're going to light the chamber of your rocket engine. So if you have a small enough engine, you can probably get away with just using a spark plug. But once you pass a certain point, that just won't provide enough energy to start the combustion reaction, start the self-sustaining combustion reaction. So at that point, you need some other, higher energy method of ignition. And the two that I've come across that seem to work well is either using an augmented spark igniter, which is what we chose to use, where you basically flow a little bit of, that's what this is right here. You flow a little bit of fuel and a little bit of oxidizer into a separate small chamber and ignite that with a spark plug. Like, these are very low mass flow rates, like maybe 1/100th of what goes through your main chamber, such that they can be lit by a spark plug, and then that creates enough energy to light the main chamber. I will say, for an augmented spark igniter, it is much easier to achieve combustion in the ASI with just the spark plug if one or both propellants are gases. Ideally, both would be gases, because you're not, at least in this case, you're not using any sophisticated injection technique. There's just a simple orifice that sets the mass flow rate for both, like a simple like orifice fitting, I think here and somewhere downstream here. So we chose to use gaseous oxygen as the oxidizer for the ASI, even though we're using nitrous oxide as the oxidizer for the main chamber. Because we're pulling the liquid phase nitrous as the oxidizer for the main chamber, it is possible to pull gas phase nitrous from the same tank or from a different tank, which could work well for you. But we chose to just use gaseous oxygen, and that has proven pretty reliable to light pretty reliably. For the fuel, we just used the same ethanol that we use for our main propellant as well. So the fuel is common, but the oxidizer is different, and you only really need a little bit for a few seconds, so it's not a ton of GOX to carry on a flight vehicle in the future. But that's proven to work pretty well for us. It is probably possible to light a liquid augmented spark igniter, but we have not been able to demonstrate that, so that we'll leave that as an exercise to the reader. The other common ignition mechanism that seems to work pretty reliably is a solid motor cartridge, where you use like an Estes solid rocket motor, very small solid rocket motor, as an igniter. And Halfcat has demonstrated that with good success as well. So this is from their website, from their guidebook. I'll link that in the description as well. You sort of it seems to be more beneficial to plumb it in from the injector face, from the top of the engine, rather than stick it up the throat. Although you can do that as well with some kind of pyrotechnic igniter. But this seems to work better, is to use a solid cartridge through the injector into the chamber. And this is just some kind of Estes solid rocket motor, a very small one, and some fittings. So that seems to work well, but again, that's a single-use system. You'd have to replace the solid rocket motor every time, and if your chamber doesn't light, you'll have to take it apart and replace that before the next firing. Whereas an augmented spark igniter, you're only limited by the amount of propellants you have, assuming your spark plug stays intact. But yeah, and it seems that you can. I mean, this is pretty compact. This whole engine is only like 3 inches in diameter. Yeah, I mean, 2.5, and then at the largest, it's a little over 3, and you can still fit an augmented spark igniter in there. So, yeah, those are the main design considerations. We also have this load cell adapter that threads into a pancake style load cell. That's good for taking force measurements. For small engines, this is how I would recommend doing it. A pancake style, small to medium maybe engines. Once you get past a certain size, I don't know if one single bolt would be the best way to do that, but there shouldn't be any significant side loads. So that's how you could take some force measurements for your engine. And then you can see we have some pressure transducers here as well to take some other pressure readings of the fluids at various stages. You can also add thermocouples that we have elected not to do. But with metal printing, you could easily add a bunch of ports along the cooling channels if you wanted to take some thermocouple or pressure readings at various stages. If you could get a lot of good data out of that. Cheap metal printing really unlocks a lot here. I will say, for small engines, one problem we did run into with metal additive was that our cooling channels were so small that the powder from the powder bed fusion process, this was printed flange side down, so it was printed like this with the flange down, and when they cut it off, some of the powder is still trapped in these channels, and they're very small grains of powder, and depowdering them can be kind of a pain. And for us, it proved very difficult. Our cooling channels are only, on this engine, our cooling channels were 0.7 millimeters wide slot channels, so they were constant area channels down the whole length. And that was the kind of channel that gave us the best, cooling results in RPA, but it turned out to be very painful to try to depowder these channels for such a small engine. So I'd recommend using bigger channels if you can, if you're going the metal additive route. Potentially printing it nozzle side down instead of flange side down might help you. If you can add some depowdering ports, I've seen a lot of people have added, you can make a port or a little sort of port off of each cooling channel to blow out the powder from, and then you can machine them off at the end when you face it. But yeah, those are some considerations. Another option is to use what's called a chamber saddle jacket design, a CSJ. This is what we've all pivoted to recently for that reason and other reasons. Let's see if I can. So, I guess I can't isolate this. So if you see this chamber, this is the metal printed part, the chamber, and now the slot channels are open. They're open face, so there's no space for the powder to get trapped into in this design. And then you just add a sort of this part is called the saddle that goes over the throat and makes it nice and cylindrical, and then the jacket closes it out, and this can be machined pretty easily on a lathe, or even printed if you really want to. But the nice thing about this is that there's no small spaces for the powder to get trapped into. You can just brush it out of these open channels and then close them out later. Of course, you pay a mass penalty, but that's one way to get around the problem. And you can see it shares the same injector design as the old engine, just with a few extra O-rings and a snap ring here. But yeah, that's about all I wanted to talk about. If you have any questions, leave them in the comments about my engine or my design process, anything else you can think of. And I'll link all the resources that I mentioned down in the description. Thank you.